Friday greetings, everybody. I've started the recording just so everybody knows, and I'm about to try to share my screen. Can anybody see my screen?
Make no sense when they come out, riding in your slipstream. It's better than I ever dreamed. Do you know where you're going? Do you know where you've been? Is that what you were thinking? That this would never end? Take my hopes and I ran.
Okay, good. So everybody can hear me and everybody can see my screen. Is that correct? Okay, perfect. Just a quick announcement before we dive into the lecture. I've added these lecture slides to Moodle. I've also added the recording of the last lab, so yesterday's lab, to Moodle. So you'll see a link to those items, and they'll be there, until the end of the semester. So you can go back and watch those lab demonstrations again if you need to. If for some reason you get stuck with your version control or something like that, you can always go back and reference those demonstrations. Okay, I'm going to try to manage my screen real estate so that the slides are big, but I can still see the chat. Let's see if this works. Okay, good. I hope everybody can read that. If you can't read the slides or you have trouble, please let me know. Also, please interrupt anytime with questions or comments. You can use the chat or you can use your microphone. It's absolutely fine. So for the next few lectures, we're going to go into depth on the topic of object-oriented design. We're actually going to take a little journey that describes how you get from the requirement specification to your design, your object-oriented design, and then from your design to your implementation. And we're going to be answering some really interesting questions along the way. I will just predicate this with the note here. A lot of the material we're about to see is from these two books, Designing Object-Oriented Software and Object-Oriented Design, Roles, Responsibilities, and Collaborations. So a lot of the ideas and the examples come from these two books. So we're going to look at some extremely fundamental questions about software. For example, how could we go from a software specification to a software design? What does that transition look like? What we've done so far, generally speaking, is just said, produce a UML diagram that shows the design of your software. But there are actually a series of intermediate steps that you go through from the specification until your final design. UML does not describe the process of object-oriented design. It just communicates the end result. So it's like, here's my result. How did I get there is one of the questions we're going to be talking about. Another topic we're going to talk about is how can we transition from a software design to an implementation, right? If we have a design like a UML diagram, how do we take that UML diagram and actually transition it to an actual implementation? We're gonna talk about very, very fundamental questions like, when should we introduce a new class? When should we introduce a new method? Are there guidelines for writing good classes and methods? Which methods belong to which classes, right? These are all decisions we have to make. How big should a class be? How should classes and methods be organized? These are very, very fundamental questions. Now, we have skimmed on these topics before. These topics are not foreign to you, but we're going to go into each of these topics in more depth than previously. So you can think of this as a depth-oriented, object-oriented design set of lectures. So we're going to really go into detail. And especially with this last question, how should classes and methods be organized? If you think about a large software project, right? Pierre mentioned the Linux operating system, which has millions of lines of code. And this is very common. Big projects consist of millions of lines of code. The central question is, how do you organize millions of lines of code? That is the central question we're trying to answer. And the answer is non-trivial. So we're about to delve into some design principles which are all about code organization. And it's a double-edged sword, because on the one hand, the concepts are not very difficult. But on the other hand, very, very few people understand these concepts and know how to put them into practice. It's shocking how seldom this information is actually put into practice, and there's a lot of evidence for this. So when you work at your first job, there's a very good chance you'll be working on a failing project. So there are some statistics like 65% of all IT projects fail. That number is always changing, but it's always greater than 50%. Sometimes you can find 75%, sometimes you can go find 55%. But actually, the reality is that most software projects fail. And the other reality is you're going to probably work on a failing project when you go out into the real world. After you take this module, though, if you apply what we're talking about in this module, you will be able to recognize how to tell if you're working on a successful project or a failing project. And I'm also speaking from experience, by the way. So I've worked in 3 different software development departments, and in all 3 of those departments I was working on failing projects. So it took me some time to understand how to recognize when a project is succeeding and when it's failing. But by the 3rd job, I knew I was working on a failing project in the first few days that I started the job. And it's because of the things that we're about to talk about in the next few weeks. So this is looking back a little bit. This is a little review. What is an object? This is my definition of an object. There are many different definitions. An object is a set of closely related data and methods that operate on that data. I'm going to introduce some new terminology that you may not have heard before, or services. So this is Bob's definition of an object. An object knows what it is. It has the information it needs to know about itself, and it knows its responsibilities and how to fulfill them. So we're going to talk about this in more depth as time goes on. And it knows how to perform the tasks that other objects request of it. It knows its own role with respect to the whole system. It knows how to fulfill its own responsibilities. And it doesn't know how to do anything else, right? We call that information hiding. Okay, so somebody needs to mute their mic. So this is, some of these slides are a little bit review, right? Objects are associated with encapsulation, which Pierre has talked about, information hiding. We're going to go into depth into message passing, which is some terminology we haven't used very much so far. Pierre also talked about polymorphism, classes and instances, and inheritance. We're going to briefly mention those, and those will be reoccurring themes over the next weeks. So this is some new terminology that we're going to use. Messages. So a message is something that an object sends to another object for a request, right? In reality, it translates into a method call, right? So for example, object A sends a message to B, object B. Object B performs an action that may involve returning some results. This is something we call a message, right? We're also going to use this term behavior a lot. So the behavior of an object is the set of messages that the object responds to, right? So we're going to use the term behavior a lot in these weeks. And method, a function performed by an object as a result of a valid message. So this methods and messages are basically synonymous, right? And a method signature is that top line of the method, right? It's the method name, the input parameters, and the return parameters. That's something we call a method signature. Maybe some of you have heard that term already. Maybe for some of you it's new. It never hurts to review that kind of terminology. Again, you've heard these terms classes and instances. So Pierre mentioned this. I'm going to mention it again very briefly. It's always nice to hear the way different people express these same concepts. Sometimes a concept doesn't sink in the very first time you hear it, and you have to hear it multiple times, maybe from multiple different sources. So the way I think of classes and instances is software often needs a system that many copies of a given kind of object, right? So we need to organize several instances of the same kind of object, right? A class is a set of objects that share the same behavior, right? We're using these terms that we just mentioned in the previous slide. It's a generic specification of all these objects that share the same behavior. So a class is really a template that defines objects. And then an instance is a member of a class, the object itself, right? So it's an instantiation of a class. For example, you could have a class called tire specification, right? And every time you instantiate a new tire, you get a new tire instance, right? Every car has 4 tires. So you can think of the tire specification as the class or the template, and then the actual manufacture of that round rubber object, an object or an instance of a tire. I hope that helps. Oh, somebody asked a question. I didn't get any beeps. I thought the teams would make some sort of a beeping sound if somebody... So why do so many projects in the real world fail? This is actually a simple answer. It's because of two reasons, essentially. Developers don't understand object-oriented design. What does that mean? It means that they don't understand the organizing principles behind a large project. Right? You have large projects, and the larger something is, the more work you have to do to make it organized. An analogy I like to use is a library. So a library, some libraries have millions of books in them. I went to a university, the University of Massachusetts, and the library was 25 stories. 25 stories, every story was full of books. That library had millions of books. If you have something with millions of books, like a library, you have to dedicate a lot of effort into the organization of all those objects, right? You can get a degree in library science that describes how to organize a library. If you think about it, if I take a book, a random book, and I walk into the library and I put that book in a random place, that book could easily be lost forever. There's no way to search a 25-story library of books to find a missing book. If you put a book in the wrong place at the UMass library, it can be easily lost forever. And that's true about object-oriented design, bad software as well. The other major reason is coding conventions. We are going to talk about coding conventions. Projects that don't follow coding conventions generally fail. So if you don't follow coding conventions and you don't have a careful organizational system, then your project is it's 99% on its road to failure. And there are lots of failing projects. Here's a typical class hierarchy. This is also looking back, right? Here's a parent class called figure, and it has the responsibilities to draw, to return the area, to return location. It has children that inherit these responsibilities to draw their own area, to return their own area, their own set of vertices, right? Circle is another kind of figure that has a draw method, and it returns an area, but it has a new responsibility, that is to maintain its own radius, and so on. And Pierre has mentioned this. We're going to talk about class hierarchies as well in more depth. This is just a little class hierarchy using this new terminology of behavior and responsibilities, essentially. Here is an overview of the object-oriented design process. So going from the specification, which is sometimes written, it's not always written down, by the way, sometimes it's verbal, but theoretically you start with a written specification, and then you go through these three major phases to get to your implementation, to start your implementation. The first major phase is initial exploration, so that's finding and identifying classes, their operations and collaborations, so the patterns of communication between the classes. Then there's a detailed analysis where we build class hierarchies from the existing classes that we identified in stage 1. And then in stage 3 we design subsystems, right? Subsystems are classes that carry out a related purpose. They collaborate to carry out a related function or a related purpose. And this is an iterative process, right? This is not linear like the waterfall method. It goes in circles. And as a developer, actually, you're thinking about these things all the time. You're thinking about things like, should I introduce a new class? Where should I put this method? Like, what class hierarchies make sense? Is my intelligence distributed in an even fashion, or is it centralized intelligence? Actually, if you're a good developer, a trained developer, you're always thinking in the back of your mind about organization. Is the organizational structure that I'm developing making sense, right? Is it logical? Does it follow any of these principles? So stage one is the initial exploration, and we're going to go through all of these stages in more detail. So we start out by identifying candidate classes in our system, given our requirement specification. Then we identify responsibilities. So those are the operations or the methods and the data that we need to carry out those responsibilities or those operations. And then we start assigning responsibilities to classes, right? And this is also starting to look at the patterns of communication between objects and classes. So let's jump right in. These are guidelines, very important guidelines for identifying objects. So if you're given a specification that's written down on paper, there are a few very important guidelines that you want to follow when you're introducing objects and classes. And hopefully most of you are familiar with these guidelines. Some of you might be seeing them for the first time. Some of you might know them. Some of you might have seen these guidelines but didn't really see them stated explicitly in black and white. So guideline number one is classes correspond to nouns. This is a general convention. This is an object-oriented design convention, and it's a universal convention. For example, vertex is an example of an object. Guideline number two is use singular nouns by default, right? Vertex is a singular noun, right? Methods correspond to verbs. So vertex draw is an example of a method, right? So the next guideline is to identify what a class does. And this word what is in boldface, right? When we're identifying classes and objects in the design phase, we do not focus on how a class does its job. The answer as to how something works or how a class carries out its responsibilities is postponed until the implementation phase. There's no point in having long, never-ending discussions about how a class does its job. That is up to the person who actually implements the class, right? Because for a given template or a given design, there are an infinite number of different ways to implement that. For every object, we identify the information or the data that the class needs to carry out its function. And we also eliminate redundant classes, right? If you start with a requirement specification and then you're introducing new classes, you'll find out that natural language contains a lot of synonyms. Okay, what does multiplicity mean? So multiplicity corresponds to collections. So a very common mistake is when naming objects to take the letter S and add that on to the name. So for example, imagine we have a tire object. If we want more than one tire, it's a bad convention to name a class tires. Just adding that letter S onto the class name. So multiplicity means more than one of something, multiple instances of something. If we want a class that's responsible for multiple instances or multiplicity, we want the name to reflect that. And here's an example, vertex collection. So we would not introduce a class called vertices. This would be bad practice. Vertex collection is singular, right? It's actually a singular noun. Collection is singular, but it's a class that's responsible for managing a collection, right? And another possibility would be vertex manager, right? A vertex manager implies a class that's responsible for managing a group. Vertex group would be another example. And by the way, if you were thinking, oh, I would like to see more examples of how to name my objects and my classes, does anybody have any idea where you would look? That's a question for the audience. Anybody feeling courageous and want to try to answer that question? The question was, if you're looking for examples on good objects that follow these naming conventions, where would you look? Anybody? I'll have to answer the question myself. A good, yes, language docs. You would look at the Java API, right? In the last lecture, I brought up the Java API in my web browser very briefly as an example of the Java doc output. But if you look at the Java API, all the objects and methods follow these conventions. So have a look at those for examples. This is really, really simple, actually. What I'm saying, some of you might be thinking, this is really simple. And it is. It's because it is simple. But it's very surprising how few people understand this and know this and follow this convention. Yeah. Stage 2 is analysis. So examine classes and responsibility to define classes that share behavior. So you're looking for shared behavior. Shared behavior maps to shared code and shared methods, right? The more shared code and the more shared methods you have, the better, right? Can one object be made a child of another? Can two objects be made a child of another? Can we introduce new abstract classes that raise the responsibilities up one level so that they can be shared? We look for ways to streamline collaboration. So collaborations between lots of objects can be complicated, right? It's the term that's sometimes used is spaghetti code. There are ways to simplify the collaborations between classes that we're going to look at. And we're also going to look at how to distribute intelligence. Intelligence is another word for responsibilities, right? A class that has lots of responsibilities has a lot of intelligence. And we don't want a class that has too many responsibilities or too much intelligence. Right, in the ideal world, the intelligence is distributed evenly and the responsibilities are distributed evenly throughout the classes. That's the goal, that's not the reality, but that's a target that we want to aim for. And then the final big stage is identifying subsystems. So after we've gone through the initial exploration and analysis stage, Stage 3 is identifying subsystems. So A subsystem is a set of classes or other subsystems that collaborate to fulfill a set of responsibilities. Right? When you hear this word responsibility, think of a method and the data that's associated with that method in order to carry out a given task. So a heavy collaboration among a set of classes may imply the need for a subsystem. And we're going to talk about, we have a lecture just on subsystems, right? We have lectures on all of these topics. So a subsystem is another organizational unit, right? And you can, or it's important as an organizational unit for designing your software, right? It can simplify complexity, it can hide or encapsulate complex collaborations and complex behavior, and it increases the potential for reusability and code reuse, right? We're going to talk about that in more detail. I will take a quick pause. So some more terminology we're going to be using in our object-oriented design discussions is client-server model and terminology. So the object-oriented design is really a set of clients and servers, or it can be thought of as a set of clients and servers, or looked at through the lens of clients and servers. So object collaborations are one way. One object requests the service of another object, usually with a method call. The client object requests the service, and the server object receives the request and provides the service, so a return value, for example. And that interaction is something we call a contract, or it's a collaboration between two objects, right? One client object requests the server of another client object. For example, you can imagine an object called time, and that object time has the responsibility to return the current time. So any client might ask the time object, please give me, please, you wouldn't use please give me the current time, like get time, right? And it returns the time. That's an example of a contract. The object that's requesting the current time is the client, and then the time object in this example is the server, right? So clients and servers are roles that objects play. An object can be both a client and a server, so generally that's true. Usually objects are both clients and servers, depending on what they're doing at a specific time. And the client-server concept keeps track of the relationships between two objects at a specific time. This is why the collaboration is one way. So the client object calls the method, calls a method of another object, and that's the collaboration, or the so-called contract, right? And each object can be part of many different contracts. So contracts is really the word that we're using to define this pattern of communication between objects, right? When one object requests the services of another object. That's what we're using this term contract to describe that. Okay, that was just a little introduction to the object-oriented design process and what we're about to look at over the next few weeks in detail. Are there any questions so far? It was a little bit like a review of some concepts and also an overview of some concepts to come. So there's a question, are there two-way collaborations? Generally, no. Generally, the collaborations are one way. That's because, at least in the programming paradigm we're looking at, an object calls the method of another object. A two-way collaboration would be like two objects calling each other's methods at the same time. And that's something we don't want. We don't want that kind of a collaboration. We always want a client-server collaboration. Actually, we don't want two objects acting as clients and servers at the exact same time, right? And if you think about it, why, like in terms of implementation, why is that? It's because when I ask, if I'm an object, for example, maybe I'm an object called date, and I'm collaborating with the time object. When I call the method getTime, I want to specify something like, maybe I want to specify the time zone. And then the time object is going to return the time to me. How could you have two methods that are both passing messages and receiving data at the same time? You wouldn't want to do that. It would be too confusing, right? So it's something you'd want to avoid. However, an object can serve as a client or a server at any time. The roles can flip and switch back and forth as long as it's not at exactly the same time. So objects alternate between client and server regularly. I hope that helped. So now we're going to, yes, classes can be both clients and servers. Yes, definitely. So let's look at responsibilities and let's talk about what we mean by responsibilities. So we're going to be using this term responsibility a lot over the next few lectures. There are two kinds of class responsibilities, the knowledge maintained by an object and the actions that are performed using that knowledge. Right? You can think of knowledge as data, or usually that's member variables, that translates into member variables of an object, and actions usually translate into methods. Right? So methods and the data that's necessary to carry out those methods. That's what this term responsibility means. And class responsibilities represent the purpose of an object in a greater system, right? Time and getTime represent a responsibility, right? So class responsibilities define services provided by an object to the system or to other objects, right? This includes information that an object can return to any client and an action any object can perform for a client object, right? That's the server perspective. And responsibilities only represent publicly available services. So those are the services that clients can see from outside the class, as opposed to private methods or private services that are only visible inside a class. So that's an important distinction. Other knowledge and actions may be needed by a class, but the definition of those should be delayed. So that means private methods and private knowledge or private data. And again, I'm repeating myself here. I put in bold-face font at the bottom. Concentrate on what a class does, not how it does it. Right? If I'm designing a class called time, I can concentrate on what the class does, but not how it does it. Because the reason is the what a class does is more important than how it does it. The how can change over time, but the what we want to stabilize, right? Implementations change over time, versions change over time, efficiency changes over time. How is decided at the implementation phase by the person who is responsible for implementing that class. A lot of people make this mistake of jumping into how something is supposed to work too soon, and then the discussions spiral out of control forever, right? And it's just not a productive use of time. In the design phase, it's all about concentrating on what a class does, not how it does it. Okay, these are some guidelines for identifying responsibilities. Again, there was a slide about that was guidelines for identifying objects, right? This is like part 2 of the guidelines. So we already had some set of guidelines for identifying objects. Now we have a set of guidelines here for identifying responsibilities, right? So given a specification, a requirement specification, we look for verbs in the requirement specification. So each active voice verb may indicate a responsibility. And one good exercise is to turn passive voice sentences into active voice sentences and have a closer look. When we're scanning the requirement specification, we're also looking for information nouns. So we're literally reading the sentences in the requirement specification, and we're going back to grammar school, and we're identifying nouns, verbs, and information nouns. Does anybody remember the definition of a noun, by the way? Can anybody remember the definition of a noun from their grammar school, their primary school? This is really actually very easy, but people forget it. Somebody said a thing. That's partially correct. I learned this in my primary school in, I think, 1st grade. What is a noun? Did everybody else go through that same process? I just assumed that everybody went to the same curricula that I did in primary school. A person, place, or thing. That's the definition that I learned. Yes. A person, place, or thing. Well done. I don't know how to pronounce your name. But yes, that's a noun, right? Like I said, this stuff is actually simple, but people just don't know how to apply it and apply it to object-oriented design and how to organize their large software projects using this knowledge. So a noun is a person, place, or thing. A verb is an action, right? An action word. So in step 2 here, we're examining information nouns in requirement specification, which is a special kind of noun, right? This might become an attribute of a class or a part of a composite class. Information words can imply how much of something, how many of something, or how big of something. For example, 10 millimeters of water, for example, right? That's an information noun. And step 3 for identifying responsibility is to perform a system walkthrough, right? You've heard of walkthroughs before. A walkthrough is actually simple and complicated at the same time. It's simple because it's like how does the software behave as you use it? But it's difficult because you have to use your imagination to imagine how a software is going to behave as you use it, right? And UML has a special set of walkthrough diagrams. I personally don't like walkthrough diagrams that much. If I'm thinking about a system walkthrough, if I was to perform a system walkthrough, I wouldn't use a UML diagram. I would use a set of screenshots. So what does the start screen look like? What are the options available on the start screen? What happens when you hit the login option? What does the login screen look like? So your walkthrough is actually a set of screenshots that show the behavior of the software and what the user sees in each stage of the process. Right, so postulate a variety of scenarios and execute the system. Scenarios should be based on a functional view, the user base, that's what I was just describing. And look for places where something happens based on system input. Right, you're always looking for input and output. Has every action been noted, and have responsibilities for each action been identified? And remember, responsibilities correspond to methods and the data that those methods need to carry out their functions, right? Yeah. Okay, I'm thinking about taking a break soon. I guess we'll do this slide and then take a little break. So we had these 3 stages to identifying responsibilities. There's one more stage, re-examining candidate classes. So we have the requirement specification, the guidelines on how to identify candidate classes. Now we're identifying the responsibilities, and we want to look at those candidate classes and identify.
I'm muted.
I got muted. Thank you for letting me know. I have no idea how I got muted. No idea. That is so weird. I don't think I pressed any buttons. Okay, I think what we're going to do now is take a little break and then resume. So let's take a break right now and then resume at 1600 hours, so in roughly 10 minutes. Yeah. I'll see everybody. Oh, right, so somebody muted me. Yeah, okay. Let's resume in 10 minutes. Thank you for letting me know I got muted.